All right, kids, we're going to begin a section 16.2 on vectors. I don't know that you've seen vectors before. You kind of might have seen them in geometry, but somehow I doubt that. But anyway, they're really not that crazy hard. They're just something new and different. Kind of like the last section, 16.1 was parametric functions, and they're something new and different as well, but they really aren't that crazy hard. So this is kind of a similar difficulty level. This is the second section of 3 in Unit 16, so we've got one more to go for this unit. And then we have Unit 17 has 3 sections as well on polar functions, and then we're done. So this one and 4 more to go, and then we can have a party. Okay, so here's the deal with vectors. In some quantities we deal with, only the magnitude or value or number is important. Your speedometer tells you how fast you're going. These are called scalars. If we're concerned about both magnitude and direction, length and direction, then we have a quantity called a vector. So here we go. This is an important sentence. Both magnitude and direction, that is considered to be a vector, because you might have said, well, we're on a section talking about vectors. What's a vector? There you go. To reiterate, with a scalar, only magnitude is important. With a vector, both magnitude and direction are important. So there are many ways to represent a vector. We're going to learn several. The first is the geometric interpretation. That's the one we're going to start out with. An example of which is shown above. In the geometric interpretation of a vector, we use a there goes Levi, a directed line segment to represent the vector. So the starting point of the vector is called the tail or the initial point. Starting point. And the ending point of the vector is indicated with an arrow. It's called the head or terminal point. Oh, good Lord. He sounds so vicious. He's really sweet. The length of the vector is the vector's magnitude. So the length is the magnitude. That's a new word for us. And the direction of the vector points... Did I say that right? And the direction the vector points is the vector's direction. There we go. Two vectors are equal if they have the same magnitude and direction. So that's important too. All right. I'm going to see if I can quiet this dog. Hold on a second. You can't be barking while I'm recording, buddy. There you go. Go somewhere else and bark. Okay, so let's try again. If a vector is in the plane is equal to the vector with an initial point of 0, 0 and a terminal point of v1, v2, then the component vector form v, see how it's bold? That's one of the notations that means vector when they bold print it, is v equals, and they use these pointy parentheses to talk about vectors. You know it's a vector when you see these pointy parentheses. v1 comma v2, where v1 and v2 are components of vector v. v1 is the horizontal component, in other words, like the x value, and v2 is the vertical component, like the y value. The vector 0, 0 is called the zero vector. Go figure. All right, so here's what we have. Let me put that in English for you. You've got a component form for a vector, and it looks like this. It's your change in x as the first value, comma, the change in y. They look a lot like coordinates. You know, we have an xy coordinate kind of plane going on. They look a lot like that. So change in x and change in y. But they've got pointy parentheses at the end. The first guy is considered your x component. Second guy is considered your y component. I think they use the words horizontal and vertical. The horizontal component, all right, you're moving in an x direction. The y component would be the same thing as your vertical component, moving in a y direction vertically. And the way that you calculate these, this is really important, the way that you calculate these is you take whatever the terminal point is, terminal vector, and you subtract away the initial vector. All right. That's going to be important to us. So you'll see how this works in action when we get into the next problem here. The other thing that they brought up is this crazy guy over here called the zero vector. A zero vector is 0, 0 in your vector symbol there. So there's the things that they kind of were talking about in that sentence. So let's see how they work in action. Let A equal 0, 0, B is 3, 4, C is negative 4, 2, D is negative 1, 6. Show that the vector U, bold printed, equals the vector A to B, and V equals C to D. Show that they're equal to one another. All right, so what we're going to do is we're going to figure out the magnitude of, or what the value would be for vector AB. So what would that look like if I take and figure out the value of the vector? So what I'm going to do, here's what it looks like, by the way. A is at 0, 0, if I were to graph it, and B is at 3, 4. 3, 4, here it is. If I were to draw that vector, it goes like this. It has direction, so I'm going to put an arrow with it. This is point A, this is point B. All right, then I have, well, we'll just deal with him first. So if I take the vector and figure out where it lands, or what my deal is with this guy, it's the terminal where it stops subtracted with the where it starts. Terminal minus initial. So the terminal place for the x's is 3. It started at 0. The terminal place for the y's is 4 minus 0. And so what I do is I just subtract them, and that tells me that I've got 3, 4 is the value of that vector. So now I'm going to go for the vector CD that they want me to compare it to. So if I figure out the vector CD, that starts at, C is at negative 4, 2, and D is at negative 1, 6. Starts here, goes here, has that direction. Well, that vector, if I do terminal minus initial, is going to look like this. Terminal x is negative 1 minus my initial x is negative 4. And be careful, it's minus and negative, so watch your signs. 6 is my y in the terminal side. The initial was 2. And so I have negative 1 plus 4. Well, darned if that isn't 3. And 6 minus 2 is 4. And you can see those two? You have just proven that they are equal to one another. And so I'm going to answer their question. Therefore, vector AB is equal to vector CD. They have the same values. Even though they're located in different parts of the coordinate plane, I might as well label this since I labeled the other one C and D. All right, there's example 1. Example 2, before we get there, there's some notation to take note of with this guy. There's a few different ways vectors are represented using notation. One uses a terminal and initial points like we just were doing. This notation indicates that the vector starts at point A and terminates at point B. Okay, we saw that. Another notation requires the naming of the vector, such as vector U. A third way is similar to the previous, but instead of using an arrow, bold print is used. We saw that on the front page as well, that bolded U or the bolded V. The notation here is the notation for finding the magnitude, the length of the vector. So if I have this notation with either single slash signs or double slash signs, it's talking about the length of the vector. The location of the vector doesn't matter. If the vectors have the same length and same direction, they are equal no matter where they are located in the coordinate plane. We just saw that in that example as well. A vector with an initial point at the origin is said to be in standard position. So in example 1, the vector AB was in standard position because A was at 0, 0. All right, for the magnitude, this is your formula. The magnitude, I'm going to take my highlighter again. The magnitude or length of a vector is taking this big old square root, or you can take whatever your V1 term is, the first term in your vector, square it and add it with the second term in the vector. And that's kind of a shortcut way to look at these. So if you're looking at, we know that in a coordinate plane, if I'm finding the distance between 2 points, the length It's the distance formula. But with vectors, you can do the same kind of thing, but just take first term, your x term squared of the vector, plus the y term squared of the vector. So that's your formula. And then it says, okay, we'll use that to find, in example 2, find the magnitude of u. Now see, they used a bold printed u. They're talking about the vector. So if this is what the vector equals, and I want to find the magnitude, how long it is, the length of it, magnitude of u is what they asked for. All I need to do is take the square root, and because this is a vector, take your x value, square it, take your y value, square it, put it in the square root. 49 and 4 is 53, so my answer is the square root of 53. Done. That's easy peasy. Number 3, find the magnitude of this guy. Well, this one takes a little bit more doing. You have to first figure out what the value of that vector is. What is that vector? This is that terminal minus initial, so 5 minus 1 gives me the x, or the v1, the first term. Negative 1 minus 2 gives me the second one, so this vector is 4, negative 3. If I want to now put the magnitude of that, I usually just use the single slashes rather than the double, but they mean the same thing. All I need to do is take the square root of each of these pieces. 4 squared plus negative 3 squared, that gives me, ooh, it's pretty, 16 and 9, square root of 25 is 5. And so we have just figured out, find the magnitude. Yep, we did. All right, there's that page done. Flipping again. We're looking at the unit vector. That's the next thing. The unit vector is a vector whose magnitude is 1. Well, that makes sense. It's kind of like the unit circle whose radius is 1, right? If I'm calling something a unit, it's got a value of 1. Its magnitude is 1. To find the unit vector in the direction of a given vector, divide each component of the vector by the magnitude of the vector. For example, if the vector v is not the 0 vector, then the unit vector is the direction of v, which is this formula right here. This is going to come into play when we look at some questions that they ask us a little later with tangent lines and such. Also in the next example 4. So it says, find the component form of the vector with an initial point P and a terminal point Q, the length of the vector, and a unit vector in the direction of the vector from P to Q. They're asking us for 3 different things. And I know that's a lot of wording and you're trying to decipher what exactly do they want me to do. So the first thing they want me to do is figure out what PQ is. What's that vector? This is the whole terminal minus initial. So Q, negative 5, minus a negative 3, my x value in there. So minus a negative 3 makes this plus 3. And 2 minus 4. I need to know what that vector would look like. So it's going to be a vector that is negative 2, negative 2, when I do that little addition and subtraction stuff. That's the first part. The second part says, all right, well, what's the length of it? What's its magnitude? Well, remember, that's just a square root of those values added. Negative 2 squared plus negative 2 squared. 4 plus 4 is 8. It's a square root of 8. Do you have to tree that and change it? Nope, leave it as the square root of 8. That's perfectly fine. All right, then they said find the unit vector. Well, if I'm finding the unit vector, I'm taking this, which is my vector, negative 2, negative 2. So I'm going to say u equals the vector of negative 2 comma negative 2 that I just found in the first part. And I'm dividing it by what the magnitude is. And well, the magnitude is the square root of 8. And so the result of that, if I put them in individual terms, would be negative 2 over the square root of 8, negative 2 over the square root of 8. Do you have to rationalize that? And again, the answer is no. Mr. AP is okay with the square roots in the denominator. That would be the unit vector for that one. All right. In general, for vector v, a, b, a is equal to the magnitude of v times cosine of theta, and b would be equal to the magnitude of v times the sine of theta. These come directly from the right triangle trig. So here's what the story is with this. If I were to go back and think about our pre-calc time, and here's my triangle in the first quadrant, where my central angle is theta. if my x value is a and my vertical value is b, this guy here is going to be the magnitude of v. So I have a couple formulas I can derive from that, thinking about my SOHCAHTOA days, right? I know that the sine of theta is the opposite over the hypotenuse, and I know the cosine of theta is the adjacent over the hypotenuse, right? Remember all those SOHCAHTOA things? Now, I could also take this thing and figure out what b actually is. If I solve for b, get it by itself, I've got to multiply both sides by this magnitude of v. So it could also be written this way. These are equivalent equivalent forms. They both are saying the same thing, they just look a little bit different. All right, there it is. You're probably going to use these two formulas more than you will the original ones. So that's why they kind of solve them out. So here's a question that would use something like that and how it would be worded. You want to do this when you're looking for an angle. So find the component form of the vectors v of length 3, magnitude of 3, that makes an angle of pi over 4 with the positive x-axis. So if I were to look at a picture of what they're talking about, it would be this kind of a vector coming from the center, has a magnitude of 3, the length of it is 3, and the angle here is pi over 4. Can you figure out what the vector is? Well, sure you can, because the vector is made up of A, this guy, comma B, this guy. So if I have that information, I know that A is the magnitude of the vector, 3, times the cosine of the angle. Well, the cosine of pi over 4, right? Let's keep going with that. Do you know what the cosine of pi over 4 is? I hope you're saying yeah. Square root of 2 over 2. So this guy is a 3 square root of 2 over 2. That's my A value. My B value I'm going to get from the second formula. Take the magnitude of the vector and times it by the sine of the angle. The length is still 3. That didn't change. Sine of pi over 4. Well, lo and behold, the sine of pi over 4 is also the square root of 2 over 2. And so I get the same answer for A and B. Will that always be the case? And we say nope. Just so happened for this guy. There's Levi. 3 square root of 2 over 2. 3 square root of 2 over 2. This is my A, this is my B, and you've answered the question. Find the component form of the vector. There it is. Okay? So that takes care of that page. We're on to the next page. These are operations with vectors, things you can do with them. You can add them, you can subtract them, you can multiply them, you can do all sorts of crazy things with them. So this is a pretty important box, and I did grab my highlighter with this one. This whole box is pretty significant. Let me take you through it. So the first thing, the zero vector, of course, is when they're both 0, 0. We know that. The stuff off to the right is the easier, it's kind of the explanation of the math gobbledygook of this, okay? So the stuff off to the right. I can add x components with x components and y components with y components. I cannot add an x and a y together. Okay, so it's x's with x's, y's with y's. I can subtract them as well. Again, x's with x's and y's with y's. You can see that with how they set up the example. I can multiply them by a constant. They call a constant a scalar. If I have a negative constant, it reverses the direction of the vector. In other words, it's going the opposite way. So that's kind of important. If you've got a negative, it's going to go in the opposite direction. When we get it in a second to drawing these, you'll see what that means. Whenever you add or subtract vectors, it's called, the result's called the resultant vector. So if they say, you know, find the resultant vector, then you're adding or subtracting those vectors together. Now these are relatively simple. If I want to know what 2u plus v is, I need to figure out what 2 times u is. I want to do that first. So you go to the u guy, 1, 3. I need 2 times the vector 1, 3. That gives me, multiply it by each piece by 2, gives me 2, 6. But then I need to take that, that's only this piece. If I do 2u plus v, now I need to take that answer and add v with it. So x and x, 4 plus 2 gives me 6. Y and y, 7 and 6 gives me 13. That's my answer. Literally, you're taking the x's and doing what you need to do with them, and the y's and, you know, keeping them consistent, not mixing the two together. So if I do a u minus a v, let's see what that would look like. If I have my u vector, 1, 3, minus my v vector, 4, 7, when I put them together, it's going to be 1 minus 4, my x's, and 3 minus 7. And so I get the resultant vector of -3, -4. And that's my answer. Now, if they said v minus u, then you got to switch these up. It's going to change things up. So the order matters. Now, this one was kind of interesting. I have no issue finding 1/2 of u. Let's see what 1/2 of u would look like. Take half of you guys. You got a 1 and a 3. So it's going to be 1/2 and 3/2. But that's not all they're asking you for. See the lines there? That means that you're really looking for the magnitude. So once you find that vector, you have to now take it and you do your magnitude formula to it, that square root. So you're going to have the square root of 1/2 squared plus 3/2 squared. Well, that would be 1/4 and 9/4. So that's the square root of 10. Oh, can't see me. The square root of 10 over the square root of 4, which would be the square root of 10. The square root of 4 is 2. And that's your final answer. Can you cancel inside of there? And the answer is no. This guy's inside, this guy's outside. You can't mix them. Okay? So that's your final answer for that. All right, next task is to try drawing these things, which is kind of fun. If I look at this, they want me to sketch the indicated vector using vectors to the right. So here's the A vector, here's the B vector. B vector is going horizontally. This A vector is kind of going in a diagonal there. So they want me to take A plus B. So I'm going to first draw A. Here's my A. I'm going to call it A. And then B goes off from that where you stop off horizontally. You connect them. You need them to be connected together there. Okay? So A plus B would be this. That's the picture that starts it, but the actual answer is connecting where you started to where you stopped. That is actually the A plus B part. All right, second one, 2A. Well, A goes like this. Now you make it an estimation. If you make it a little too long, you make it whatever, it's fine. This is A, but then I'm going another A. Now this one doesn't have an enclosure like the other one did. I didn't have to close it in, but 2A would actually be starting here at your starting place and stopping here. This would be my 2A value. They usually use dotted lines like I'm doing to represent that vector. Now if I do, this one's kind of interesting. If I do A minus B, let me do the A first, right? You got the A, we've got the A down. Here's A. We know that B is a horizontal, but look at this. What kind of B is it? It's a negative B. That means it reverses direction. So instead of it going off to the right, it's going to go off to the left horizontally. That's my B. And so now I can connect them with the starting place to the stopping place. That value is A minus B. So be careful of the negatives. All right, last one on drawing. My A, here's my A. 2B, well, B goes off to the right, and I got another off to the right. Here's my B and B. If I connect my beginning initial spot to my ending spot, that would be A plus 2B. And that's how you draw these things. So kind of cool. They're kind of fun. All right, next one is to multiply vectors. Multiplying vectors is not intuitive. It's similar to multiplying matrices. There's two ways to multiply vectors. We're learning one way called dot product. That's what we're going to be doing. And the second one's called the cross product, but actually that doesn't come into use until Calc 3. So you don't need to worry about that yet. So we're just going to do the dot product, and here's the rule. The rule says the dot product of vectors u and v is take the first term of u and multiply it with the first term of v, add it with the second term of u times the second term of v. So we're really looking at this right here. This would be an alternate form, but really if they're asking you to multiply them, this is the format we're going to use. So if I say to you, and they didn't really give you a good example of this, so I'm going to make one up for you. If u is the vector 2, 5, and v is the vector, hold on, is the vector negative 2, 1, and they say to you, find u times v, here's what it would look like. U times v equals 2, first term here, times the first term over here, negative 2, plus, I'm following this, the second term, 5, times 1. All right, so what is that? Negative 4 plus 5. I get an answer of 1, and you have just multiplied them. So you get single answers for these. I guess just kind of like you do when you're doing the adding or whatever. Angle between the vectors. This one comes into play a little bit. I'm looking for the angle. I set up the cosine of theta is the multiplication of the two vectors times the magnitude of the two vectors multiplied together. But then if they're actually looking for the angle itself, don't forget when you're looking for an angle, you have to use the inverse trig functions there, the cosine to the negative 1. So you're going to end up, again, it's the same formula, it's just cosine to the negative 1 of that. And you'll see how that works in just a second in this next example. Example 8. Find the measure of angle ABC determined by the vertices 0, 0, 3, 5, and 5, 2. So what I did was I just did a quick little sketch because I'm all about the visual. So A was at 0, 0. B was at 3, 5. Here's B at 3, 5. And C is at 5, 2. I want to know what the measure of angle ABC is. Now, if you remember from geometry, it starts at A, goes to B, B is the vertex, and then ends at C. So my angle is this angle here. Find the angle. Here's theta. So here's what you need to do to be able to find the angle. You have to know what each of those vectors are. So I'm going to create the vector for u. I'm going to create the vector for v. So u is going to be my vector going from B, my vertex, to A. That's this guy, this leg, right? So it's coming from the vertex and going through A. So if I look at that, this guy would be, let's see, I'm going the terminal side. Remember, when I did this example, I did it totally backwards when I was doing my work because I forgot that, remember on the front page where we started, it's the terminal minus the initial. So I'm reminding you of that so you don't make the same mistake. So it is going from 0 to 3. So 0 minus 3 gives me a negative 3. And then my y's are 0 minus 5 gives me a negative 5. My v vector is the other one here from B to C. Right, makes the other side of the angle. Same thing, it's terminal minus initial. So 5 minus 3 is 2. And 2 minus 5 is a negative 3. But that's not all we need. That's my u, got my v. Now I need to know what their magnitudes are. So I'm going to go back here and I'm going to find the magnitude of this guy. The magnitude of u. Well, that's just the big old square root of these guys added up. So -3 squared plus -5 squared equals 9 and 25, so I get the square root of 34. And my v vector, the other side of this, magnitude of that is 2 squared plus -3 squared, gives me 4 and 9, so I've got the square root of 13. So let's put it together to figure out the angle. The angle is going to be the cosine of theta equals u times v. Did we figure that one out yet? No, we didn't. Let's do u times v. Well, it's going to be, take the x's. Let me erase this so I have space. So if I do u times v, it's take the x's, multiply them together, so -6. -5 times -3 is +15, and I add those two things. So -6 plus 15 is 9. Now I can put it together. See how I've got u times v, and I've got the magnitude of u times the magnitude of v. That's what the cosine of theta would be. So it is 9 over the square root of 34 times the square root of 13. I want to know the angle, so in my calculator I'm going to put cosine to the -1. That's the notation I'm going to have. Cosine to the -1 of this hot mess. And that's going to pop out what the angle is. Now if you're in radians, which I think most of your calculators probably are, it's 1.128 radians. They did not say whether it should be in degrees or radians, so either answer is perfectly good. I want to say the answer was like 60 degrees-ish, in that neighborhood if you happen to have it in degrees. All right. The next one says, we're almost done, the examples anyway. Find the unit vectors, tangent and normal to the curve, defined by the parametric equations, yada yada, at the point where t equals 4. I'm going to show you one of these. I'm not really too concerned about them because I don't think they really come up much in the exam. I don't think I've ever seen a question like this on there. So I'll just, since there's several of these on here, I'll give you one to show you what they're talking about, and then we'll see what we think from there. So here's what you want to do. This one is dealing with, when I look at these, the unit vector, and I think this came up back in the notes in one of the boxes up above. But if not, here's what the deal is. Unit tangent vector. A unit tangent vector has a formula that says take v of t and divide it by the magnitude of v of t. So in other words, you are you're going to figure out what the derivative is for these guys, right? V of t. So I'm going to look at my first term here and I'm going to figure out what his derivative is, x prime. X prime would be 1/2 t, so it's just a 1/2, taking the derivative. If I take a derivative of the y term, y prime, this is the square root of t, so t to the 1/2, so it's going to be 1/2 t to the -1/2, or 1 over 2 square roots of t. Now when, did they give me a t value? They did, when t equals 4. So I'm going to take 4 and plug it in. Now this has nothing to plug it into. So my result for the first x prime is just a 1/2. If I put a 4 into this guy, square root of 4 is 2. 2 times 2 is 4. This becomes a 1/4. Well, that's this. That's this piece right here. So now I'm going on and I'm going to figure out what the magnitude of that is. Well, the magnitude is the big old square root thing, right? So it's 1/2 quantity squared plus 1/4 quantity squared And I am going to simplify that. 1/2 squared is 1/4. 1/4 squared is 1/16. When I add these up, I get the square root, and simplify it. You got to get common denominators, so what does this become? This becomes 5/16. This would be 4/16, and one more is 5/16. So it would be the square root of 5, the square root of 16 is 4. Well, if I have my resultant vector, 1/2, 1/4, divided by the square root of 5 over 4, isn't that the same thing as multiplying it by the reciprocal? So my tangent would be 4/5, or 4 over the square root of 5 times 1/2, 1/4. So that gives me a result of 2 over the square root of 5 and 1 over the square root of 5. But interestingly enough, and this is where it gets a little goofy, like this part up to here is not that big a deal. Interestingly enough, if I were to create, there's actually 2 tangent vectors, and the other one goes the other way, the opposite direction. So it would be -2 square root of 5, -1 over the square root of 5. And the normal guys, normal would be perpendicular. So if I perpendicular, here's what happens with them, and this is kind of goofy. You use the same values you got here, but this becomes a -1 over the square root of 5, they switch, and 2 square root of 5. And the second one is 1 over the square root of 5, -2 over the square root of 5. And you can see they're kind of goofy. So I kind of like the problem until I get to here, and then this gets a little wonky with these, but that's how it works. All right. Example 10 is one more like that, but again, I did all the work for it. Let me just show you and explain it real quick. So I do the same thing. I find the derivatives, I simplify the derivatives, I put in the t-value they tell me. T-value they told me was 1, so I put the 1 in. That gives me 1/2 for this guy, and it gives me 2 for this guy, 1 plus 1. So this is my tangent vector. And I go along and I figure out what the magnitude is for that, square root of 17 over 2. But since I'm dividing by that, it actually is multiplying by the reciprocal, so I'm multiplying my vector by this magnitude, and then I get this. So this is my resulting tangent vector there. So the unit tangent is going to be positives of this and negatives of this. The normal vectors, they switch places so that your x's and y's are switched, and you've got signs that are a little bit wonky there, but that's your answer for that one. So it's done exactly the same way. But again, I haven't seen those on the exam, so I'm not so sure that you really need to know those very much. Example 11 with these Boeing planes and such, we're not going to do those. So you can skip example 11. That gets us to, let me see where it gets us to. I'm going to come over and look at these, my answer sheets. These are already uploaded on our page. So I started doing the first homework. By the way, there's 3 homework days. There's a homework 1, 2, and 3 for this section. I'm only going to make you do parts of 1 and 2. You do not have to do 3 at all. So let me show you what I'm talking about here. Number 1 I started to do, but then I realized it was from section 16.1. I was like, we don't need to do that. So same with number 2 and same with number 3. They're all from section 16.1. But then number 4 you can do. This was calculating vectors, simplifying them. So that one's okay. Numbers 5, 6, and 7 on the next page, they're all in this section talking about vectors and adding them, or coming up with the component vectors, drawing them. So 5, 6, 7, they're fine. Number 8 is one of those tangent normal line things, so give that one a shot. Number 9 is the airplane flying. You don't have to do that. That's it for homework 1. Homework 2 has the same situation, day 2. You can see that one. Again, you've got the first 3 are from section 16.1. You don't have to do that. But number 4 starts this section, so you're going to do number 4. Number 5 is 16.1 again. You don't have to do this. This is all posted, so you can see it. 6 and 7 are good. That's part of what we're doing now. 8 is back to the tangent and normal lines. 8 I had some issue with because as I did it, I got answers that are here following the same thing we did in the examples, but the book answers were slightly different. So again, just I wanted you to have exposure to that. Maybe somebody like Sairaj might want to actually figure out why it is that the book answer is what it is. I couldn't figure it out, and I tried to go into other calculus books and it just didn't help. So there you go. There's that one, the challenge. Then homework C. This one is totally optional because I think you've got enough practice doing the problems that we have. All right. So I also attached on the classroom page the answers to all the optional questions. So if you are interested in trying to do those, the answers are posted so that you can check yourself. Okay, that starts with example 11 that we skipped, and then goes through the homework problems and things that we skipped as well. So it's all scanned and into our classroom page. As always, shoot me an email if you have any questions, and I will get 16.3 up shortly. Thanks for all your hard work. I'll see you in class.